Hello, I am Reetika Joshi. I am presenting here our recent work, Twist Transfer to a Solar Jet from a Big Flux Rope Detected in the HMI Magnetogram. This work is done with the collaboration of Dr. Brigitte Schmieder, Guillaume Lanier, Veronique Baumier, and Ramesh Chandra. In this study, we analyzed a multi-wavelength observational analysis of a solar jet to understand how the twist is transferred to the jet from a big flux rope. So, solar jets are detected throughout the entire solar cycle in a wide wavelength range from extreme ultraviolet to X-rays. And interestingly, they are observed with the unwrinkled threads of dark material in the H alpha. We call them cool surges. These jets are propagating with a very high speed as the collimated plasma ejection along with the open magnetic field lines. Magnetic reconnection is believed to be the main trigger mechanism behind these jets, and magnetic flux emergence, flux cancellation, and magnetic instability are the trigger mechanism for the magnetic reconnection. In the process of magnetic flux emergence, the magnetic flux emerges from the photosphere and it gets reconnect with the pre-existing coronal magnetic field, and this reconnection this emergence produce a favorable condition for the magnetic reconnection and hence for the eruption of the solar jets. These surges and the jets are occasionally reported in the observations as well as they are simulated in various models. Recently, Viper et al. Reported a case study where the reconnection can be happen in a magnetic field region in the photosphere where the magnetic field vectors are nearly parallel to the polarity inversion line. They called this region as the bald patch, and it supports for the reconnection to be happen in the for the solar jets. To have a look for our case study, we did the multi-wavelength observational analysis of the solar jet with the Solar Dynamics Observatory and Interface Region Imaging Spectrograph IRIS observations. This active region is the result of a collapse between two emerging magnetic flux regions overlaid with the arch filament systems well observed by AIA and IRIS. In the magnetic field maps, we found that it is evident a long sigmoidal flux rope in the neighborhood of the jet region. We also did the spectral analysis of magnesium 2, carbon 2, and silicon 4 for, from the iris spectra. And finally, we compared the MHD simulation, the ohm MHD simulations with the observational analysis. This is the active region observations in AI 304 angstrom. So we can easily see it is the jet base and the jet is ejecting in the westward direction and having some dark material or the surge in between of it. This jet was associated with a GOES B6.7 class flare. These are the multithermal images from the AIA observations. So in the first column, we have seen that there are the contours, the magnetic field contours of strength plus minus 300 Gauss. And these are the observation from 94 to 304 angstrom. The jet is well visible in all the wavelengths. So the jet is here, this bright one, and this dark material is the surge which is embedded in the bright branches of the jet. We also observed some arch filament systems like that, and also the long loops at the jet base. The base brightening is enlarged here. We also found a dome-like structure, dome kind of structure at the jet base. To understand this active region more precisely, we did the magnetic field evolution of the active region. So this is the magnetic field of the active region. We see there are two main patches, this negative patch and this positive patch. So from this big negative patch, there are small negative polarities which are moving in the south direction, and collapsing with the positive part of this big positive region. This positive region is moving in the upward direction and the negative part was moving in the downward direction. So in this way, there is a shear present between them. If you look at a zoom view, so this is the emerging flux region 1 and this is the emerging flux region 2. This emerging flux region 1 mainly mainly consists the main part of the active region with the leading negative polarity and the following positive polarity. And this another emerging flux region 2, EMF2, we call it EMF2, there are small patches of the negative polarity. So after that, this positive part is going up and this negative part is going down. After some time it got elongated and it looks like that. So we see that there is a shear between this positive part and this negative part, and this small bipole formed, which we will see later that it is exactly at the jet reconnection point. This is the iris analysis of the jet. It is iris carbon 2 slit jaw image movie, which comes from the temperature 30,000 Kelvin. So this jet is associated, it is seen that it is associated with the rotating structure as well. Here are the AI 304 angstrom observations and the carbon 2 observations and magnesium 2, which comes from 5,000 to 20,000 Kelvin. The reconnection point, the X point, is shown here. So the interesting thing is that iris scanned the active region with the 4 slit positions, and the slit 1 position was exactly at the jet location. So it is the position of slit 1. So this slit crosses the reconnection point, and with the different pixel values of Y, we can make the spectrum analysis. So here it is. It is the AI 304 observation of the jet where this cool part is embedded in between of them. This cool part is because of the absorption of 304 angstrom emission due to the helium continuum. And we see that this is the position of slit 1. So, so the spectrum of this corresponding to this region is this one. We see that there is a blue shift as well as red shift in the magnesium spectrum, and the absorption is seen here. So it is the case in all the wavelengths. It is for magnesium, it is for silicon, and it is for carbon. So the as I have mentioned earlier, there are 4 slit positions. So this is for slit 1, slit 2, slit 3, and slit 4. So as the slit 1 is exactly at the reconnection point, so it is well visible that this is the blue shift and it is the red shift, and it is well visible in all the wavelengths. So for the maximum extension of this red and blue shift is at y is equal to almost 80. So we call it the reconnection point, and when we analyze them with the spectral analysis, it is here when we see at the inflection point there is a blue shift from around minus 300 kilometer per second to minus 100 kilometer per second, and a red shift from 80 kilometer per second to 100 kilometer per second. We also did a more detailed iris spectral analysis, which is also published in this paper recently. So to understand well the flux row formation and the twist transfer connection, we did the vector magnetic field analysis of the solar jet active region. Here we did the vector magnetic field map with the UNOFIT inversion code. This vector magnetic field map presents the full magnetic field vectors with 3 components in the heliospheric frame of reference. The vertical component of the magnetic field are presented with this color table, and 2 horizontal components are associated to form the horizontal vector represented by the arrows. If we see the zoom view of this bipole, which is exactly at the reconnection point, we see that we clearly see the motion of the negative patches in the downward direction, and to make a small bipole, we call this bipole like JP1, J, and 2, as J stands for jet. So if we see in this small bipole region, we will see that the direction of the arrows are from negative to positive, and it is a evidence for the bald patch region. We compare our observations with the MHD simulations generated with the Ohm code of Alanier 2005. We proposed here we proposed to compare our jet observations with the MHD simulations, where the physical conditions are favorable to produce a flux rope. These two are the observational analysis with HMI data and prepared with the UNOFIT inversion code, and these two are the observational results from the simulations. So we have seen that a big flux rope is observed at the PI polarity inversion line, where the vectors are nearly parallel at the polarity inversion line and are converging at the bottom of the flux rope, which is evident for the bald patch region. And it is exactly the same results in the simulations as well, where the vectors are inclined parallel here and converging in this direction. So the presence of the flux rope is supported by the HMI pattern of the transverse fields and vertical current density maps, and in the MSD simulations as well. The vector pattern of observations and models are strongly near parallel to the polarity inversion line and converging together in the bottom part. To well understand this whole scenario, we proposed a sketch of the flux rope, where the flux rope is shown in between of the two regions P1 and N2 with this solid black line, where it is extended towards the south and making a small bipole, this JP1, JN2. A bald patch current sheet is formed in between of the overlying arcade of the flux rope and the magnetic field lines of the emerging flux regions. This bald patch current sheet can be converted into a null point after some time, and this null point is heated at all the temperatures, and because of it the jet is expanding in the westward direction. Here in the panel C, we propose that the dark material was embedded in the bald patch region, and it also shows its evidence presence of evidence in the iris spectrum with the blue and red shift. So we conclude that the flux rope was extended towards the south, and due to the small scale photospheric surface motions, the twist was transferred from this flux rope to the jet. And after the ejection of the jet, a remnant part of twist was remained in the small bipole region, and the rope was not erupted. So our results are: the active region was a result of collapsing between two emerging flux regions. A large flux rope in the vicinity of the jet region was detected, and it was supported by the MHD simulations and the observations as well. The magnetic topology of the active region explains that it was a bald patch region, and afterwards it was transformed to a X-point current sheet. The fast extension of the flux rope due to photospheric surface motions provides a possibility to the transfer of twist to the jet. And the iris spectra at the reconnection site shows a tilt in the spectrum, which is evidence for the rotating structure. This transport of twist from the flux rope into the jet is observed in the iris spectrum as well. And our magnetic field analysis with the UNOFIT code and the comparison with the simulation provides a strong evidence for the flux rope formation. The iris spectral profiles are very useful tools for explaining the dynamics such as temperature, density, and the rotation in the jets. And we also did a thorough investigation of the iris spectrum analysis, and it is also published as this paper. These are the references. So thank you very much for your kind attention. It is our paper in which this study is thoroughly explained. Thank you.